Continue.
Got it? Okay.
Recording in progress.
Is it working?
Yeah.
Perfect. So good morning, everyone. So it's a great pleasure to be back together again. So I mean, can you hear me without the mic? Yeah. Okay. I will stay here just for the mic of the thing, right, of the recording. So it's great to be back again. So thanks for your, for attending this. It has been 2 years. I mean, it was a whole mess, but hopefully it makes us all strong. And now, like, for example, the ActivityNet team is also strong. We are back and we wanted to do this in a hybrid manner, online and with you guys. So let's do it. Just to remind you, like this month we are celebrating Juneteenth speech. This year, June 19 and 20 marks Juneteenth, a U.S. holiday commemorating the end of slavery in the U.S. and a holiday of special significance in the U.S. South, like New Orleans, right? We encourage attendees to learn more about Juneteenth and its historical context, and to join the city of New Orleans in celebrating the Juneteenth holiday. Please, you can find more information in the website of CVPR, so let's move ahead. So for those of you who are not aware, like the challenge organizers are the crew of cows, Human, Fabian, like who is the heart and brave soul behind the challenge, myself, Victor, Chaimal, Frost, and in addition to that, we also have, like in previous year, the guest task organizers, David, Surish, Afsal, that is with us today, Silvio, Anthony, Katsuki, Yogesh, and Akash. Thanks thanks to all of them for participating and making the video community great and stronger. The challenge organizers, like as usual, Kate Snook, Juan Carlos, and Bernard. We really want to thank all of our sponsors, in particular the Demo Alibaba, the Damo Academy, Google AI, and Chaos, because without their sponsorship and funding, we couldn't do this. Now, why are we interested on doing video understanding? Okay, we have we can say like all these really nice applications: cooking, assistance for people, security, self-driving. We also have, like, with the internet era comes new ways of interacting with video as well. So we have YouTube Shorts and all that kind of business that the cool kids use. And all of that is impactful because we are changing the way that people interact. And that's the main reason of using video, is that images are static at the end of the day, right? We need, video is more pervasive, and that's the way that basically everyone is communicating these days, through video and audiovisual data. Now, what is the workshop about? ActivityNet task. We provide what we call the ActivityNet task. So that are two: temporal action localization and dense event captioning. For those of you who are familiar with the event, you have already discovered these tasks in the previous years. In addition to that, we invite the community to join us and push the frontiers of video understanding through new challenges, new benchmarks that will enable our researchers to develop new algorithms. For example, we have the AVA challenge, the Active SRL, SoccerNet challenge, Tiny Actions, Home Mesh. And this year we will have two keynote speakers. One is Mike Shou, who will join virtually, and Du Tran, who will be here. So for those of you, please let your friends know that are here. Please let your friends know about it, because you will have the opportunity to engage with Du, which is like a very interesting character in our community. The schedule is gonna be the schedule in the morning. Here is the welcoming and opening remarks from yours, Victor. Then we will move to the keynote, and I really invite you to attend the 7 years of ActivityNet talk, which will be given by Fabian, my best friend, and Frost, that is also on the line. So please join us. Then we will discuss the results about the ActivityNet challenge and the AVA challenge. We will go for lunch, have fun, network, and come back to Active SRL challenge, discuss about SoccerNet results, We will have the keynote talk from Dutran, again in person, so please join. And then we will discuss the results of the Tiny Actions Challenge, Homemade Challenge, and the closing remarks from the organizers. Without further ado, I would like to introduce Mike Shou. Mike Shou is a tenure-track assistant professor at National University of Singapore. He was a research scientist at Facebook AI in the Bay Area. He obtained his PhD degree at Columbia University in the city of New York, working with Professor Chi-Fu Chang. He was awarded Wei Family Private Funding Fellowship, and he received the Best Student Paper nomination at CVPR 2017. His team won the first place in the international challenge, including ActivityNet 2017, Ego4D 2022, Epic Kitchen 2022. He is a fellow of the National Research Foundation, NRF, in Singapore. He's on the Forbes 30 under 30 Asia list. So basically, Mike has a really strong record. Please listen to his talk. I personally, like, for example, by the time that I was doing my PhD, we were working on a very similar topic. So I was always reading his papers. I'm really looking forward to the things that he has for us today. So without further ado, let's move to his talk. Oops. Is it not? Ah. Let me show here. Frost, can you see the?
Victor, I can see the window. Now it's not in full screen.
Ah.
This is like a tricky thing. Let's just stop sharing.
Ah, yeah, screen share. Yeah. Oh, yeah. The screen share the whole video. It's duplicating and screen share.
Mm-hmm.
And you have now the system preferences. Now you're.
Yeah, but I cannot see it.
Ah, you cannot see.
This is very tricky. Okay, cool. I think we can just.
Colombian style. That's how you provide.
Let's just do this.
We hope it can be transferred to not only many data.
How do we play now?
Oh yeah, I can see the screen.
You can see the screen? How do we play?
Yes, in full screen mode.
Hello, everyone. This is Mike from National University of Singapore. Thanks to the ActivityNet organizers for the invite. Today, I'm going to talk about our recent work on large-scale video language pre-training. This joint works with my students at NUS and also other great collaborators. This is a quick outline of the three works I will introduce today. But first of all, why large-scale pre-training? Over the recent years, large-scale pre-training has become a popular machine learning paradigm. It achieves impressive results in natural language processing, computer vision. Notably for multimodal pre-training, there has some famous work from OpenAI, including Click, DALL-E. This new machine learning paradigm is interesting because one pre-trained model can be easily adapted to various downstream tasks. Specifically, there are a lot of video caption data on internet. They might be noisy, but easy to obtain a large quantity of them. With such video text pair, we can design some pre-training tasks like text to video matching and train a model based on such massive data. This process is often referred as pre-training. Once it's done, the pre-trained model can be fine-tuned for each downstream task individually. people found that with such pre-trained model as initialization, we often only need a small amount of training data for each downstream task. With minimal task-specific fine-tuning, we can achieve even better results than state-of-the-art. So that's great. And let's first take a look at the data part of VLP, video language pre-training. One popular VLP dataset is How to 100 Million. It contains YouTube videos and their transcripts. It's great, it's very large, but the temporal alignment might not be that accurate. Actually, it's often noisy because it's just from YouTube transcripts. WebWith, new dataset released last year, has much higher quality text, but the size is relatively smaller, yet still good for VLP. And for the model part of VLP, there have been several works already over the recent years. Early works in the VLP are mainly based on extracted features, not really trained in an end-to-end manner. Like in the ICCV19 video bird work, they use a bird-like architecture. They import tokens, word embeddings, and video frame features. They use masked token modeling, basically mask some input tokens and then try to recover it in the output. Similarly, in iClear21, we have this SSP model from Facebook, which is also using extracted video frame features, but trained with contrastive learning. In CVPR20, the ActBird work from UTS not only use frame level feature, but further incorporate local regions. In a nutshell, but all these are not end-to-end. So researchers want to make the end-to-end, which as expected would learn better representation. In the last year, there are quite a few new works like Clipper from Microsoft and Frozen in Time from Oxford. They have a visual encoder that takes raw pixels as input and train end-to-end. Clipper specifically use ConvNet for video embedding, while Frozen is the first to use transformer. But interesting we have observed is that all these end-to-end models operate at the frame level. None of them leverage object information or region information. Actually, there is a strong correspondence between object region in the video and object tokens in the description sentence, right? Like in this example, a little girl dancing to music and a teenage girl using a computer. You can see the strong correspondence between the tokens, the word tokens, and the bounding box detection result from fast RCN. And in fact, it's no surprise that modeling object could be useful. End-to-end vision language pre-training based on these object regions have actually dominate image text pre-training. Like this unit model from ECCV 2020 for each input image, it actually first used fast RCN to extract, say, 30 region proposals that are object-centric. And then for each input token is essentially the cropped and the scaled object region. So why not video? There are two reasons. The first one is very expensive in terms of compute for video. Say for 10 seconds long video, even with just a sample 1 frame per second, we have 10 frames. And for each frame, typically we would need like 30 box proposals. So it's very expensive. And also over frames, over time, there is a high redundancy, which makes the optimization actually kind of challenging. So to overcome these issues, we want to sort of like maximize the local region information we can obtain for improving VLP. Meanwhile, we are trying to minimize the number of, actual number of regions that we need to compute and use. So we strive for such a balance and develop a solution. This is actually a joint work with my student Alex Wang. It's a CVPR 2022 work entitled Object-Aware video language pre-training for retrieval. So let's first recap what does the conventional end-to-end video language pre-training model like, frozen in time look like. It has two streams, one for visual encoding and another for text encoding. In our implementation, actually for the visual encoding, we use the transformer, which is a space-time vision transformer based on VIT that can encode a set of sampled video frames. And specifically, this CAS token to be learned as the output, the corresponding CAS token is supposed to be the visual embedding for the whole video. For the text string, we adopt this tailbird, and similarly, there is a CAS token as the output, which is the embedding for the whole input sentence. Now, for the visual part, we want to incorporate object region information somehow. But to keep the computational cost affordable, we only model object on one single frame, which is referred as anchor frame here. On this anchor frame, we do bounding box detection using a fast RCN model that is trained on visual genome for 1.6K categories. Then we mask out the background region on this anchor frame, and the masked frame is treated basically in a similar way as how we process the original video frames, but in a separate string. Then with the single anchor frame as input, we have a specific visual embedding for this input anchor frame. Meanwhile, for the bounding box detection result, we want to make use 4 of them. Then we do something on the text side as well. Basically, we concat the object text, sort of like as a new sentence, fit into the same texture encoder. This becomes another text string, and we can get a texture embedding for this object text string as well. Now let's take a look at the full model, basically 4 strings. One for the sampled video frames, a sequence of frames, one for the anchor frame, one for the object text, and one for the captioning sentence. Each string will produce an embedding as the output. So traditionally, we only have video text matching between basically the first video string and the last capture string, typically using congestive loss. With our new design for modeling objects, we could have 2 more matchings. One is the matching between the first string of video and the object text, and another matching is the matching between the anchor frame string and the last caption string. Then basically we can have a matching here and a matching here. With such a new model, object-aware transformer, our full pipeline is to first pre-train it on large-scale video text pre-training dataset like WebV. And then for each downstream task, say MSRVDT, it has its own train set and also its own evaluation set. We would fine-tune our pre-trained model on MSRVDT's training set and then evaluate on its test set. And similarly, we would do this fine-tuning on another dataset, MSVD, so on and so forth. Note that such object strings, basically these 2 object-aware strings, are only used for better representation learning during pre-training. When we adapt it to downstream tasks, neither fine-tuning nor inference we have. Basically, we remove these 2 object strings and no need to run object detection at all during the inference. So the inference model is exactly the same as the traditional model, which typically has a very high efficiency for text-to-video retrieval. So we have achieved significant improvements on standard benchmarks. Just to give some colors, this is the result table for MSRVDT. like methods, the initialization we used for the visual encoder even before the pre-training stage, and use the pre-training data, the record results at 1 and 5, etc. You can see that our method, this highlighted one, is better than like expert SSB because our model is trained end-to-end, and it's also better than clippers and frozen because we model the object origin information during pre-training. Further, we observe consistent improvement over SOTA method on 4 benchmarks. These bar plots basically indicate our against our SOTA. Different colors correspond to different data sets, namely MSRVTT, MSVD, DDMO, LS, and DC. Also, not only in the case of fine tuning, but also in another 2 cases, another 2 settings, the gains are also good. One is zero shot. Basically, there is no fine tuning on the downstream task. We just use the pre-trained model directly for embedding extraction on the downstream data. Another setting is linear probe. Effectively, we only fine-tune the last layer on the downstream task, but keep all the previous layer fixed. All right, so now we know, okay, incorporating object information is awesome, but if you notice in this OA transformer work, we only conduct experiments on retrieval, basically text to video retrieval. This is because such model design, it fits the retrieval scenario very well. Each video or sentence will generate an embedding. Then to do retrieval, basically to compute similarity, we only need to do linear product. But for other tasks, for example, QA, question answering, typically we need more complex fusion beyond linear product. For example, Clipper, Clipper uses a transformer to fuse the textual feature and the visual features. So the interesting of VLP model is that it's versatile, meaning that it can be transferred to, we hope it can be transferred to not only many data sets for one task, say retrieval, but can also transfer to many different tasks. So that's really the interesting thing of VLP, to be versatile. And there are indeed some, these versatile VLP models. For example, Violet from Microsoft, it has several separate video basically components. One is the video encoding network, another is the word embedding network, and the fusion transformer. Malot as from SMAL21 as well is versatile, but also have several components like video encoder, word encoder, cross-modality transformer. So we found that these versatile VLP models often have several separate components or separate networks. This would lead to some issues. First of all, it's relatively hard to optimize jointly. For example, the output of this text encoder might not be that compatible to the visual embedding generated here. When we fit these two into the same fusion transformer, it's hard to optimize. Second, when actually often we would like to have stronger and stronger visual or texture embedding. So we end up with iterate and using deeper and heavier embedder. While the later fusion part is often also complex, there could be some redundancy between these networks. For example, some parameter used in the fusion might be actually be able to share with the unimodel embedder, so that we can save some flops and make VLP models more efficient. Thus, we ponder, can we have all-in-one? So this all-in-one has two meanings. The first one is all components, all networks in one single network, basically this fusion, video embedder, text embedder, all in one single network. And its input are just the raw text and the raw video. And the second meaning of this all-in-one is that this single pre-trained network can be adapted to various downstream tasks, like video question answering, visual common sense reasoning, action recognition, all powered by one pre-trained model. So to this end, we develop all-in-one, exploring unified video language pre-training. Again, this is a joint work with Alex, and the code and chain models have been released. This is our framework. Similar to the previous work, the input a sequence of video frames and the textual description. After pathfinding and tokenizer, they are concatenated together. Note that besides the position embedding, we also devise a modality embedding. Basically, it's similar to position embedding. The modality embedding is also a learnable vector. We have one such learnable vector for video type input and another vector for the text type input. Then the backbone is simply VIT, 12 stacked blocks. So one novel design in this block is this temporal token rolling layer. So the motivation for this temporal token rolling layer is, the caption often actually describe contents across multiple temporal frames. A boy singing song in front of stage across reference. Then when we obtain the tokens from this input data, we would have text token, visual tokens for the first frame, the orange part, visual token for the second frame, visual token for the third frame. We want to model, these tokens all together so that we can, model the temporal frames jointly. To do so, a straightforward way is to just flatten all these tokens, like this one, and we do save attention over all input tokens. This is no doubt very expensive in terms of compute. So instead, to save the computational cost, we propose a novel token rolling operation. We basically roll some visual tokens of the first frame. Like, this is the original visual token of the first frame. We roll some part of it to the second frame. So move it from here to here. And then for the second frame, the purple one, we also roll some of its token to the third frame. Similarly, for the third frame, some of these tokens have been moved to the first frame. Then when we do save attention, we still just do save attention within each frame. It's limited to each frame. But it can still model two kinds of relations. One is the cross modality. Basically, like here we have the text token and the visual token, so we can model their relation. Basically, this cross modality relation, and also we can also model interference relation. Like here we have the tokens, visual tokens from not only this frame but also the previous frame. And notably, this operation is parameter free. We do not introduce any additional parameters to be learned, so it's quite efficient. With this new layer and this backbone, we could have the upper, and based on the upper, we have multiple pretext chaining objectives. VTM, basically the conventional video text matching, and binary classifier to determine basically yes or no. Masked language modeling for both text and video tokens. And the third one is video text contrastive learning. You may wonder how such a model can be used for contrastive learning, because contrastive learning requires an embedding for the video and another embedding for text. Yet with our all-in-one model, both video and text as inputs, one single model only produces one embedding as output. So in fact, our model can also accept just one modality as input. Basically, there's no need to do concatenation if one of the input string is removed. So then, given text-only inputs, we will get embedding for the text. Given video-only input, we get embedding for the video. And with such design, we can facilitate some downstream tasks like retrieval, which only does linear product between text embedding and video embedding, because they need to do very fast retrieval. All right, so now with all these design pieces covered, let's see some magic. On the standard task of text-to-video retrieval on MSR-VTT, we compare our all-in-one method with other sorta methods like violet, frozen, taco, clip, bird. The x-axis is efficiency, basically smaller, better. And the y-axis is the recall results at 1, so higher, better. We can see clearly that our all-in-one models not only improve the state-of-the-art recall numbers, but also has pretty low flops. In other words, is pretty highly efficient. And here are just the more detailed results from text-to-video retrieval on MSR-VTT, ActivityNet caption, DDMO. I will skip the details. And also the good results on video question answering, better results than SOTA on multiple choice selection, visual common sense reasoning, action recognition. Here we show some visualization to better understand our model. Given our input video and its paired text with some masked text token, we let the model to fill in these masked words and show its corresponding visual patch that has high attention. So like the first word is actually couple, and the second word is walking, the last one is mountains, and we can see that its corresponding visual patches that has high attention. It's good. All right, so a quick summary of this all-in-one work. It only has one single pre-trained network and saving 50% parameters compared to SOTA models. And we have this novel temporal token rolling operation, which is free of parameters. And it achieves SOTA results on different data sets like TVQA, MSVDD, MSVD, Eagle4D, and across different settings, like not only in fine tuning, but also in zero shot and linear prop. And also our codes and the models have been released already. All right, so this is great all in one, but there is an issue. The pre-training data set we used so far are often of third-person view because it's sourced from internet, from web. But for many real-world applications, like AR/VR smart glass, or for robot to learn how to perform some tasks, the video stream observed by the AR glass or robot is often of first-person view, basically egocentric. So our nature question is that would VLP model pre-trained on third-person view videos still work well for egocentric video? In fact, later on, we experimentally show that it does not. And if this is the case, if it does not work well, how can we create an egocentric VLP model? So we studied this problem in our recent work entitled Egocentric video language pre-training. This is a joint work with my student Kevin, and also many great colleagues. Previously, ego-centric datasets are of small data scale. For example, Shiraz ego, 30K number of clips, 30K number of texts, and they are domain specific, like focusing on home, or like Epic Kitchen focusing on the kitchen scenario, making generic video language pre-training kind of like impossible. Ego 4D, which is a newly released data set, and actually this year's CVPR, is pretty large and quite diverse. It really unlocks ego-centric VLP. Based on Ego 4D, we create a pre-training data set called Ego Clip. It has 3.8 million clips, which is comparable to the size of 2.5 million for WebV that we use in the previous all-in-one work, and also OA object aware transformer. So it's comparable to WebV. It's possible to do video language pre-training for ego-centric video now. And a quick recap of Ego 4D data. It contains this original Ego 4D data. It contains 3.6K hours of video. It covers everyday activities around the world. It has diverse occupations, like 80 real-world scenarios. It's unscripted. With such raw Ego 4D data, in order to use that for video language pre-training, there are actually 3 research questions we wanted to answer. First one is how to create pre-training data set of video text pairs, because Ego 4D videos are often very long. And the second question, how to design a pre-training model for such Ego VLP problem. And the last question is what benchmark actually we should evaluate our model. So to answer this question, in our work, we actually adjust them one by one. So we create a basically video language pre-training set called Ego Clip of 3.8 million video test pairs. And we propose a ego-centric friendly VLP objective called Ego NCE, kind of like extension of the traditional NCE laws to customize it for the ego-centric scenario. And the last point is that, which I'd like to actually focus on it in this presentation, is that we construct a development set called Ego MCQ. And this development set really facilitated us to, in the design of ego-centric VLP. I will skip the detail of the first 2 bullets, but mostly focus on the last one. So let's talk about why we need such a depth set. When we design the VLP model, the typical pipeline is we design the model, we design the pre-training task, and we design the pre-training data set. With all these, we can start to train a model and get a pre-trained model. Once the model has been pre-trained, we can transfer it to downstream benchmark for evaluation. And if the result is not good, we may go back to iterate and adjust the our design of the model or our design of the data set. This is kind of like the signal we use to help us iterate and improve the model design or data set design. But this is typical VLP pipeline. With such pipeline, there is an underlying issue. When the downstream benchmark is very different from the pre-training task and data set, especially at the very beginning of when we start to design the task, design the model, design the data set, if the downstream benchmark is very different, the signal we obtain from the result on the downstream benchmarks might not be accurate. And this is exactly the case for our egocentric VLP here. Our pre-trained data is in the wild, and our pre-training task is video text pair matching. But when looking at the downstream benchmarks, like Epic Kitchen, Charades, like for Epic Kitchen, it focuses on the kitchen scenario, and Charades mainly used for action recognition. And also we have some benchmarks in Ego4D challenges. There are also other tasks like moment localization, object state change detection, which are not exactly video text matching. What we like to have is in the last row here. We like to have something that in the wild and focus on the task of video text matching, basically very relevant to our pre-training data and task. So then therefore, we hope that here we can have a relevant development set. With that, we can adjust our model design or dataset design. Once the performance on the depth set is good enough, we can finalize the pre-trained model and transfer it to other real downstream benchmarks. So now we understand why we need such a depth set, and the question is that how can we construct it? Naturally, we will think of just using text-to-video retrieval based on the clip and text pair we get from Ego4D videos. But actually, text-to-video retrieval is not a good choice here. This is because multiple different videos in Ego4D could have similar captions. And these captions are often pretty short, like close the fridge. So this would lead to the one-to-many issue. Given a texture query, close the refrigerator, we would say obtain this, we will retrieve these clips. Maybe this one, the last one here is actually the ground truth clip with this label, with this texture description. But for other top retrieved results, for other top retrieved clips, they are also accurate, but just not labeled as ground truth. To overcome this issue, a tentative solution is to automatically dedupe. For example, we can use bird texture feature similarity and do some thresholding to remove these duplicated clips. But in reality, we found it to be quite ad hoc and does not work well. So in this paper, instead, we construct Ego MCQ multiple choice question task. Say if we basically only keep 5 candidate options, it's not likely that duplication happens, so that we can elevate the one-to-many issue. And also to better examine the model, basically its capability in dealing with easy case and challenge case, we have been thinking about, can we have a kind of like a easy exam and hard exam? We implemented this by proposing 2 different grouping strategies. The first one is inter-video. Basically, the options are from different videos. As you can see in the visualization here, the contents look like very different. Another grouping strategy is intra-video. Basically, all 5 options, all 5 candidates, they are continuous over time in the same video. They have pretty similar context, background, and very hard to distinguish. So with these technologies, a pre-training set Ego clip, a pre-training objective Ego NCE, and the development set Ego MCQ, we could finally obtain our egocentric video language pre-trained model. And this pre-trained model improves SOTA significantly on 5 egocentric benchmarks across 3 datasets. I'd like to maybe only go over the details for this slide. This is text-to-video retrieval on Epic Kitchen 100. If you take a look at the highlighted region here, with basically the same backbone frozen in time, just differs in the pre-training data we use. And this is the final results, like higher, better, higher, better. our ego clip, this new ego-centric pre-training data set is definitely better than how to 100 million and WebV, those third-person view data set. And also the pre-trained model transferred well to other Ego 4D challenge benchmarks, including natural language query, object state change classification, moment query. And also similarly, good results can be observed on Cheray's Ego on the task of action recognition. All right, so final takeaway. These are all these reworks I have introduced today. I hope you have enjoyed the talk and really enjoy in the future about our release codes as well. Before I end, actually, do you want something more? Here you go. The first piece is a joint work with my student Ray, video text pre-training with learned regions. So the motivation is that incorporating region information is great, like what we have done in the object array transformer. But running the object detector like FastRCN is too expensive. We, in this work, develop an inexpensive method to incorporate region information without object detection. The code has been released. And another interesting work is this one, revitalize region feature for democratizing video language pre-training. This is a joint work with my student Guan Yu. So as we know, VLP is notoriously expensive in terms of compute. We often need to train on like a lot of GPUs like for a few days. Thus we aim to democratize VLP. This work presents a method of competitive results with 80% less pre-training time and data. And its code and the trained model have been released as well. And all right, so that's really the end of my talk. If you have any questions, feel free to ask on GitHub, post an issue, or just directly email us. Thank you very much.
Amazing, right? Anyone else find it interesting? So Frost, are you there? Hi, Frost.
Yes, I'm here.
Okay.
You see me? Oh,
yeah,
no,
I will put the slideshow then. Oh, well, I mean, instead of doing.
All right. So yeah, thank you, Victor, for the kind words and introduction. And thank you all for coming. So as Victor was saying, this is actually the 7th year of ActivityNet. And I think it has been a pleasure to organize this challenge along all these years. I think we have learned a lot, and we wanted to share some of the findings and lessons that we found interesting throughout this journey. So this is going to be a joint talk. So I'm just going to be giving an intro of these lessons learned. And then Frost, who is online, will be giving kind of like a detailed talk on the lessons learned in the temporal action localization task. So let's start. First of all, I would like to make a reminder to all, why should we care about video understanding? I think that's the first question that we need to ask, why video? And I will first try to motivate this from the video use cases we deal with in our daily life. First of all, we're recording our kids, our pets at home. I mean, video is helping us to actually monitor what's happening with our the people that we love, and as well, videos and cameras make us feel safe in a way. So we have surveillance cameras. We also have cameras that monitor the traffic. So we have a huge amount of video that's actually monitoring our life. Also, video is a way to record the events that we enjoy the most. Like YouTube videos, we actually record all these travel activities, pleasure activities, and many things that basically we post online. We record events that we like carnivals or parades. we also record ourselves doing exercise, and we teach other people how to do things through video. And finally, video is definitely entertaining. So we watch movies, we watch TV shows, and these things actually keep us like happy in some way. So I will actually make a point that interacting and generating video became part of our life. So I don't think nobody will imagine like today's life without video, or like many of us wouldn't imagine our life without video. We wouldn't make it possible to actually do this hybrid talk. Today, we wouldn't have video nowadays. So it's important to actually understand what's happening in those videos, right? So that's the first point. We are scientists, so I want to make a data-driven point here. So why video is so important? Okay, if you don't care, I think I'm going to take this off. Very hard to talk with the mask. So yeah, so I'm going to make a point here. So basically, this is the traffic online throughout the years, throughout the last 8 years or so. And we see that video is like rapidly increasingly across the years. And nowadays, it's actually the main source of traffic in the internet. With more than 200 exabytes of data shared nowadays is video. So this is a huge amount of data, and we need to understand those bits and those contents that are being shared online. And of course, like more like in a application perspective, like what can we do if we recognize the content of those videos and we recognize what people is doing those videos, that can actually unlock many applications like surveillance, advertisement, elderly care, risk assessment, sports analysis, and video editing. And of course, this is not limited. I know that you may know many other applications where understanding what people is doing may actually end up in interesting applications that will improve our life. So yeah, I think this is just making a point why we thought about ActivityNet as a data set, as a challenge. And all these motivate us to actually see what was happening in 2015 in the video understanding community. So we look back at the past, like what were the first data sets in the community, in the action, recognition, and video understanding community. We first start with KTH in 2004. These were like how the video looked like at the time. So we have this kind of like very controlled scenario. You have people doing some action. It's a grayscale video. I think it's definitely a great data set, right? Because we can actually benchmark. I think was one of the first data sets where we can actually benchmark the performance of action recognition methods. But as you can see, it may have some limitations, right? So it doesn't have a strong diversity because we only have like 5 or 6 people actually being recording doing those activities. They were recorded in the same environment, and there were a handful of action categories, right? So it was limited in that sense. It also has very short and trimmed videos. There were like 5 to 10 second clips. And we know that video is more unconstrained and more challenging and diverse than these kind of videos. But definitely, this is kind of like pioneer work in this area. And I think actually sets the route towards the data sets we are seeing today. Later in 2018, another interesting data set came out, the Hollywood data set, which now has more complex scenes, right? Because now you don't have only 5 or 8 people being recorded doing these actions, but now you have Hollywood actors. So those actions are now being recorded in more challenging scenarios. They are more realistic, right? Like actors are being paid to make the events and the scenes that happen to look realistically. So this actually is getting closer, like this kind of data is getting closer to our daily life and how video is actually recorded. But it's still like movies, like if you think about movies, they are still constrained in a way because they try to recreate our life, but I think it's very hard to actually do it through movies, right? You will only capture a part of it. Later, like the UCF dataset, I think this is a pioneer work in the sense of like bringing videos from the internet. So UCF, which was recorded or like created in 2013, was one of the first datasets in the video community to collect data from the internet. Now you see like they have, for this data set, the original version has 50 different action classes, and then they expanded to 101 action classes. So you see that things start to scale up in the mid 2010s or so. Yeah, so I think it's worth it to mention this data set. Then we have the TOMS data set that was as well. It was an extension of the UCF data set, but now it incorporates the concept of untrimmed videos. So now you don't have these short trim videos, but now you have very long videos where other things different than the action you're looking for is happening. And then they introduce the task of temporal action localization indeed. So this task is basically, given an untrimmed video like the one we're seeing right now, you want to find the exact start and end time when the action is happening, in this case, long jump. Right? So we want to find the boundaries and all the instances in the video where this action is happening. So this is like a walkthrough through the data sets and the last landscape of data sets before 2015. And then in 2015, we introduced ActivityNet, where we actually try to push on diversity. We scale up the data collection part. Instead of having only 50 or 100 action classes, we expanded up to 200. And then we also just crowd a lot of videos from the internet. Those videos were untrimmed, so you also have to do this temporal action localization task. And then another component of it is like, we actually increased the diversity by a lot. All these data sets before 2014 were focusing on single type of videos. For instance, UCF and TUMOS were mainly focused in sports. But then in ActivityNet, we introduced the concept of household activities. Like we collect videos about vacuuming floor, about watering your garden, things like that, things that we do every day. I think it's great that all these data sets focus on sport first because it's healthy, but in our day, we spend the time like doing these things like vacuuming the floor, like washing the dishes and so on. So we start collecting all these type of daily life activities. So this is a snapshot of ActivityNet, like some classes, as I was mentioning before, like things we do every day, like maybe cooking, peeling potatoes, maybe some sport like playing badminton, polishing shoes, shoveling snow, horse riding, and vacuuming floor. Having total 200 actions. And yeah, so we try to scale up this and also make it like more challenging data set for the community to work with. On top of ActivityNet, we built the ActivityNet challenge in 2016 after we published and released the data. And this challenge has evolved across the years. So it has been 7 years already. And we have had many guest tasks ranging from action recognition to visual entity analysis, spatial temporal action detection, and many more. So it has been like a journey, and we have actually included many guest tasks into our challenge. And we have had the sponsorship from many different companies like and academic institutions as well. These companies include DeepMind, Google, Chaos, Panasonic, NVIDIA, Qualcomm, Adobe, and Facebook, or Meta now. So we have been, we're very grateful of the support of these companies throughout the years. Yeah, so I'm just going to wrap up here the intro of this part of the lesson learned, and I wanted to zoom a bit on the temporal action localization task, which was one of the tasks we pushed harder because in the first couple of years, we noticed like untrimmed action classification, the models were able to handle it in a decent manner, but then the temporal action localization task was one of the biggest challenges. So we put a special focus on this task. And just to emphasize what the task is about is like, even an untrimmed video, like the one we see on the top, this is just some frames from the video. The task of a model will be to actually produce the output at the bottom, right? So we wanted to detect the start and end time and what action is happening in the video. I'm just gonna go quickly, just a summary. Frost is gonna talk in detail, but this has been the performance improvement across the years in the ActivityNet challenge. So in the first one in 2016, we started with a mean AP of 17%. You see, like at the beginning, like the first couple of years, we have like enough improvements. But now it's kind of like saturating into a point where we cannot improve further the mean IP performance. So we're wondering, why is this happening? Why are we saturating? Why are we reaching this point where it's actually very hard to push further the performance of this localization task? We did some analysis on the results of the state-of-the-art models. And for the audience, for context, like what's a typical state-of-the-art model for temporal action localization is as follows. So basically, it's the model in the middle. So usually you have this on-stream video, and then you have a visual encoder that encodes clips from those very long videos. It creates a feature or visual representation, and then you have a model on top that actually grounds the start and end time of the actions that we're looking for. So this is the typical approach, and actually this visual encoder is typically trained on or pre-trained in a large-scale action recognition dataset like Kinetics. Kinetics is one of the datasets that has enabled this type of like boost in performance in the temporal action localization task. But yeah, so given that we have the context of like how the state-of-the-art model for action localization looks like, we start asking questions like, what are some things like the models are catching up, or what are things where we can actually improve? One of the things like we notice is like most of the model don't take into account context. So within this can be something maybe humans do or humans leverage to solve this task. So one of the experiments we did is actually ask humans, like instead of to actually watch what action was happening, we showed to them few seconds or like several seconds before the action happens, and we asked them to predict what's going to happen next, or what action is going to happen next. And we were surprised that most people were able to actually predict what was happening. And the reason is basically humans are able to leverage context cues to solve these tasks. But strange enough, like the models are actually not performing as well when there is a lot of context in particular actions. So what we did is we measured the context around the action of interest, and we diagnosed the performance of those methods. We found out that actually the larger the context, the harder it is for the models to actually localize the start and end points. Because like if you can imagine, as human, we have strong priors, but for the model, things look pretty similar across this chunk of time. So it's difficult for the models to actually predict the right start and end boundaries. And another thing that we found is like, I'm not going to jump into details of this, but another thing we found is like models tend to classify the action well, but the major issue is to actually find the start and end time boundaries. This is well an issue for humans in many times. It's actually difficult to find agreement for humans, but models have especially hard time to do this task. With that, we're reaching to the end of this talk, and I just want to point some route of the future of ActivityNet. I think one of the news we wanted to share today is like we're retiring the ActivityNet task for next year, but we still wanted to grow the community. So we hope we can still maybe host the workshop next year with the guest tasks, or like we wanted to organize the guest tasks around in order to keep doing these challenges over the year. But for now, we think like the ActivityNet task reaches like kind of like a point where there is marginal improvement in performance, and we wanted to give a space for other tasks to join the community. And we are really looking forward to listen from the community's feedback to see if we wanted to organize a workshop next year, gathering all these guest tasks or other tasks in the video understanding field. With that, thank you for your attention. And I'm now switching to Frost, who is going to continue the presentation.
Fabian, I will share my screen.
Yeah, go ahead, please. Let me pull you on the screen.
Share screen. Screen 2. Share. Can you see my screen without speaker note? Okay, cool.
Yep.
Hey, Fabian, remind me what's the duration of my talk? Should we
have,
strictly follow 30 seconds or 30 minutes, or we?
Yeah. We have 30 minutes. 30 minutes should be fine for us.
Okay. Okay. Thank you. Okay. So can everyone hear me clearly?
Yes, we can hear you, Frost.
Okay, great. Okay, hello. Thanks. Also, thanks for the great summary from Fabian. You know, back to the year of 2015, ActivityNet was the largest temporal activity detection dataset. And now we are in the year of 2022, and we can still see its impact in some recent datasets. For example, in Mac's talk, he mentioned the Ego4D dataset, the egocentric video dataset that covers over 3,000 hours videos. And we know for some tasks like moment retrieval or natural language retrievals, for those tasks are also like related to temporal action localizations, and we use similar evaluation metrics to evaluate models' performance. A short self-introduction. I'm Frost Shou. I started to work on this topic since 2019. I'm a PhD student. Now I'm a PhD candidate in KAUST under the supervision of Bernard Gagnon. And as Fabian mentioned, we have two observations. One is that the temporal context was not fully exploited, and also the training classification for video encoders seems too simple. So in the next, in the remaining of the talk, I will share some progress that our lab has done related to the two observations, and then I will also give some short comment on the future direction that we can do to tackle the temporal action localization task. And in the progress talk, I will mainly focus on two topics. One is how to better leverage those temporal contexts, especially for the purpose of temporal action localization. That means how to design the detector site, if you recall the two-stage figure that Fabian showed previously. And then I will also talk about on the video encoder side in the first stage, basically how to optimize the encoders, especially for temporal action localization task. So we have a kind of similar motivation from Mac's talk, which we would like to improve the video encoder for better representation learning for temporal action localization. Okay, let's start. My first topic will from GTAD. GTAD is a CVPR 2020 paper, and it works on temporal action localization. And the basic idea is based on our observation that the current activity detector doesn't exploit the temporal context very well. So in GTAD, what we are assuming is that, okay, what if we design a detector such that we can consider all the possible temporal context. So to include all the possible temporal context, we are trying to rebuild the video as a graph or as a video graph, and we cast the problem temporal action localization as a subgraph localization problem. And then since now we are in the graph domain, we can use some existing theory or operations built in graph convolutional neural networks, GCNs, and some of our operations is borrowed in deep GCNs. It's also a paper from our lab in ICCB 2019, and followed following GTAT, we also go some steps further. We have the nice VSGN work in ICCV 2021, and we talk about how to do a video self-stitching, which to magnify a short period of the video along the temporal context. And we also try to have a new graph networks that can progressively aggregate the feature, not only from the same scale, but also from cross scales. Okay, let's see how GTAT works. So I believe many of you are pretty familiar with the basic pipeline of temporal action localizations, but also for some people who are new to this domain, we in our video is usually a long untrimmed video, like minutes long, and usually we are not able to fit all of the video frames into single video encoders. So instead of that, what we do is we break the video into clips, and we have clip encoders running on each of the clip. So each clip is basically contain like 8 or 16 frames, and here it comes the first limitation on the clip encoder, which is that their temporal context is super limited. So which means in one clip encoder, they can only see 8 or 16 frames. We cannot know much further. So that's why after extracting features in the clip level, we prefer to build some detection model such that we can further aggregate features in different scale. And the idea of GTAT is that we build a video as a video graph for context, and so that each clip feature or clip representation will be a graph node, and we can try to build edges based on some principles. And the idea is that when we run message passing over the graph, we can aggregate the feature that most related to the current node. And more importantly, we can let the model to decide which edge to pick, which means which means we can let the model to decide which node is more correlated to the current node. Now there is a graph representation of the video. So you can see there are different colors of dots. We assign them different meanings. The green are the actions, and we also have a red and blue for start and end clip. And we also have the yellow dots, which means the background. So we can find the green dot can have 2 areas, which means for some videos, there are usually more than one activities, and that makes the task more challenging. So we, in the gray, the lens, we also show the graph edges. So basically there are 2 types of edges in GTAT. One is called temporal edges that connect the in the circle, which to maintain the temporal ordering information of the video. And we also have the dynamic context edge, which is discovered by the network and to automatically build the most related correlation. Okay, so now we have reformulated the problem as a graph localization task, because we only want to localize the green subgraphs in this video graph. And now let's see how can we build a solution to the subgraph localization task. Here is the GTAT pipeline. We have the input of the sequence of frames extract from the video. And after that, we have the feature extractions as explained in the previous slides, that we have clip level features. And then we have something interesting. After one convolutions, we have something called GC-next. So GCN for graph convolutional network, and GC-next is referring to the previous work ResNext, which means we have the split, transform, and merging strategy to reduce the cardinality. And if we zoom out to GC-next block, we can find it has two type of edges. So we can say it's two graphs. So because the two graphs share the same node, which are the video clip, but they have different edges. So the black one is used to represent the semantic edge. The semantic edge is dynamic. So here the implementation is based on operation in GCNs called dynamic edge convolution. And the idea is that we have a mechanism to automatically find the top k nearest representations and build an edge among them. And also, since we can apply B block of GC-next, in each block, the representation of each graph node are different, so that we can observe different semantic graphs. So the dynamic is not only shows when we go layers by layer, and it also shows that when we train the model in different iterations. So this is a semantic graph, and as we mentioned, we also have the temporal graph. We find this super useful because if we only have a semantic graph, we are losing the temporal ordering information, and the temporal graph is formulated as a forward graph and a backward graph to keep the temporal ordering. Okay, after a couple of GC-next block, we observe a new representation of the video, which tried to exploit the temporal context as much as possible. And then we applied a SG align or subgraph align layer to extract a feature for each anchor. So basically, anchor is a predefined set of actions, and the SG align is from the RI align in 2D object detections, but we apply it on the graph domain. So then the SG align will assign features to each anchor, and then we can have a simple localization module to rank all the anchors and score the different prediction. So we can train the model from the extracted features to the predictions. And here is our result on ActivityNet temporal action localization dataset. We get average MAP of 34.0.9, which in current view it's not that high. And when we compare our competitors, the improvement is also not that numerically high, but as we all know that this metric of average MAP is the average of all the classes, and then we do another average of different temporal LUs, and they are very stable, and every point of improvement is still significant. And beyond the performance, GTAD also gave some interpretations on what context is look like, and without using any human annotations. Let's see this example. Here we also visualize a graph of a video, I think arm wrestling with video. We also have the green dot to represent the actions, and we have the yellow dot to represent the background. So we show one frame of background and one frame of the action. And the graph edges are from the last layer of GC-next. And we can observe that some edges connecting actions to actions, but there are also some actions connected from actions to backgrounds. So which means that although those backgrounds are not positive activities, but they are still helpful for us to predict what activity is and where the action is. So similarly, we can find another video in ActivityNet dataset, which has more background and less foreground, and we can similarly build the video clip connections based on their feature representation. And then we do something interesting. Then we, from the two existing videos, we can generate a new video by concatenating a foreground of one video with the background of the other video. So now what we are doing is we are generating or synthesizing a new video that never exists in the dataset, where the background should be totally unrelated to the foreground. So when we have this synthesized video, we put it forward to our pre-trained network, and we can also observe the dynamic graphs. What we find is that we still maintain the semantic edges between actions to actions, between backgrounds to backgrounds, and we don't have any more information between actions and the background from the other video, because they are from totally different videos. So this is a simple video, let's say, stitching idea, but it tells us what the contexts are expected to be in the GTAT setting. Kind of following GTAT work, and we also went some steps further. We have this VSGN network, and the idea of VSGN is that we have this video self-stitching model. Remember that we have tried to stitch two videos together, but the model doesn't use the correlations between different videos. But by stitching, we are creating a new videos that it can magnify a short period of video along the temporal dimension, and then we can apply a longer temporal context. So it has a cross video context. And we also find it's helpful to have the graph convolutions that form not only the same scale, but also the cross scale. Because of the time limitation, I will not go deep to this VSGN paper. Okay, this is pretty much of the first topic. And then I will quickly go through the second topic about the clip encoders. So this is based on our observation that the current classification model is the pre-training of classification seems too much simple, and the clip encoding seems to have some issue. I will introduce three works. Those three works are very typical from different perspectives: XTC, BSP, and TSP. They all work on the video encoder pre-training, and they all give us some information on how to optimize an encoder for temporal action localization. But they are in different perspective, because XTC is a self-supervised learning method. So in SSL, it relies on big amount of data. It doesn't need any temporal annotations. And compared to XTC, BSP is more like a kind of weakly supervised learning method, which means we would like to know the class of the given videos, but we don't necessarily need the temporal annotation, which means we don't need the start of the end of the specific activities. And TSP is more like a fully supervised setting, in which we exactly do the video encoder pre-training on ActivityNet experiment. And from the experiment, we can see TSP has the strongest feature for temporal action localization. and I believe it's still very active in the challenge submissions in recent years. Okay, let's quickly go through XDC. The XDC work is based on previous paper, which is kind of like a landmark paper in SSL. It's called deep clustering. And the deep clustering idea is very simple, interesting, but effective. It's in image classification. And what it does is it takes the input images into a initialized convolutional neural networks, and then we can observe the feature representations. And then we run clustering on those feature representations to get clustering center. The center is used as pseudo label. Then we can use a pseudo label to supervise the ConvNet to make those features more discriminative. So after a few iterations, we will go over the process again. We will update the pseudo label and train the network in more iterations. In XDC, what we do is we bring the deep clustering idea in the video domain. Videos include RGB frames and also audios. And a straightforward setting is that we can have deep clustering for RGB frames, and we can also have this clustering for audio signals. So here the EV is a video encoder and EA is the audio encoder, and we can assign pseudo labels to each of them. But as I said, it's like a straightforward settings. We also studied different type of settings and try to figure out what's the best case for cross-model video encoder learning. And what we found is that in what we call XDC, cross-model deep clustering runs the best, in which we have the pseudo label from RGB images, and it is used to supervise the training for audio signal. And we also have the pseudo label from audio signal and used to supervise the RGB frames training. So after the pre-training of the two video and audio encoders, we can apply them for different type of tasks. So what we do here is we applied for action recognition. We can either freeze the backbone, only train the last layer, or we can fine-tune the entire layers. And what we find is that if we use XDC, with the same kinetics training, we have a very good performance, and also on audio side, we have a good performance. But more interestingly, if we use a larger scale data set, which doesn't have any annotations, it can us the current current fully supervised setting showing here. So from 95 to 94. So up to now, it's not that related to temporal action localization, but then we have another experiment on Thomas dataset. We also have, we still keep the video encoder fully supervised trained on kinetics, and also the encoder on XDC. And we find that we have the same observation, which means the XDC training without any human annotations can, or it's more representative than the kinetics pre-training. So XDC is have a promising result, and it make us to rethink about the pre-training of the temporal action localization task. If we consider other tasks such as image classification, we usually do the like a ResNet pre-training on ImageNet, and then we fine-tune on our data set. And if it's for action recognition, we also have this large-scale kinetics data set for pre-training. But now the issue is we are working on temporal action localization, and it seems we are still using kinetics for pre-training, which gave a big gap. So because we know the kinetics is more for action recognition, and now we are working on temporal localization. There is a big gap between action recognition and localization. So now to have one step further, we start to visualize the kinetics feature in ActivityNet videos. So in these visualizations, we show the similarity between two clips in one video. So X and Y are the temporal dimensions. We use the green signals to show the positive clips. And what we expect is that in those areas, so when we compare two clips that are both from one activities, they share more similarities. And if we compare the clip, one is from action and one is from the background, it should give us more different representations. And unfortunately, in kinetics pre-training, it cannot achieve that property. So one work in BSP, what we do is that we propose a boundary synthesis method, and based on different type of action boundaries, we can simulate those boundaries and synthesize the video by stitching two videos into one. And so here is an example. I think I have a bigger one. Yes, for different class stitching, different class boundary. This is one case when in ActivityNet, we can find some activities from making a sandwich and giving a talk. And unfortunately, we don't have such information in our pre-training dataset kinetics, but by synthesizing such fake boundaries, we can still have videos like that. Within this boundary dataset, what we can do is the following. We still have our vanilla encoder. It is used for action recognition, so it can recognize different kind of activities like long jump, Zumba, but we still have our BSP encoder. In BSP encoder, we are trying to classify different type of boundaries to make the video encoder to be more boundary sensitive. Both vanilla encoder and BSP encoder are critical or super important for temporal action localization, because we need to know both the activity content and also the boundary of the activity. Then what we do is we concatenate the features and then feed forward into any temporal action localization solution. Here we use GTAT, for example. And if we apply this method, the improvement is very clear. And remember here, we only change the pre-training. We only use the existing data set to generate a new videos and do training, and we can observe like 0.5 improvement in terms of average MAP. But interestingly, because this is pre-training, is for boundary sensitive pre-training, the method is super generic to different localization tasks. So there is a task called step localization, where the actor is behaving complicated activities such as cooking, and we want to localize every step. And it also performs well on video language grounding, where we have video and the language as input, and we want to localize the most relevant video content to the language. And to the end, we also have the TSP, the temporal sensitive pre-training. In TSP, we do it more straightforward. More straightforward means, since for now we already have the ActivityNet videos, we would like to use the TAO dataset itself to pre-train the video encoder. And the main idea is to make the representation to be sensitive to activity. So we have this besides the action label classification, we also have temporal region classification. It's a binary classifier to classify foreground and background. And from the performance, we can see the TSP gave the most boost for temporal action localization task. And we can also visualize the feature similarities. We can find after using TSP, we can observe more similar representation for activities and different representations between activity and its background. Okay, I think I'm a bit over time. I would like to spend 5 more minutes, is that okay, to give some remaining challenges for temporal action localization. Here, remaining challenges doesn't mean that the challenge I described previously is already solved. They are still issue there, but the following are more challenging. One is about the detecting short activities in untrimmed videos. Indeed, short activities more occurs in the real life, as Fabian introduced in the very beginning. Like if we want to find the memorable moment in our daily life, it's definitely a very small portion of the activity. It is super challenging. In the 2 tables, the first plot showed us the most number of annotations are about extremely short activities. But if we compare the performance, GTAD is here, and it gets the lowest average MAP. We already have work on VSGN to try to tackle this problem by extend the temporal context. But according to the performance, we can see the short activity performance, it's still behind the average, much behind the average. Our next challenge is end-to-end training. I think in Mac's video, he already talked about the challenge, why it is a challenge. But this might be some issues we need to face in the future. One straightforward idea is to do low fidelity training. So the idea is after the pre-training, we can have a sequence of low fidelity training step where we downsample the video. We can either downsample them in spatial domain or in temporal domain, and then we can have a cyclic training procedure. After that, because after downsampling, we can do the end-to-end, and we can restore the full fidelity settings. And then the video encoder is optimized in an end-to-end fashion. As a short summary, take-home message, we still need to work on localizing short activities, and we are looking for richer video clip representations, such as end-to-end training. And also multimodality for localization is also definitely a promising direction. Thank you for listening. I'm a bit over time. I believe this, we can have more questions in the Q&A session.
Thank you, Frost. So just double check, can you hear us over there?
Yeah.
Great.
Yeah.
Just wonder if there is any question from the audience for Frost. Just go ahead. You can go to the mic, maybe.
I'm curious about the processing time of one task. You talked about the graph convolution neural network for processing the video about 7 to 15 frames. How long it takes?
Were you able to get the question, Frost?
Is the question about the extra time cost in graph convolutions in GTAD? Yeah. In here, I would say it's minimal because in the graph community, they are working on optimizing the process, and we know that it takes time to find the k-nearest neighbors, that critical operations to build the most correlated graphs. But keep in mind that in our cases, the number of nodes is not that much, only 100 in GTAT case, and it doesn't take much time to do that most expensive operation in graph.
Thank you.
Yeah, thank you for the question.
All right, so I think we're running a bit over time, but thank you for us again, and thank you for the question. So now we're moving to the next session, which is going to be about a summary of the ActivityNet challenges and the AVAR challenge, and Shamal is going to host it.